Hello, am I audible? Can anyone please confirm this?
Yes, sir.
Okay. Uh, so, good afternoon, everyone, and welcome to the TA session of the course, brief course on superconductivity. So, basically, myself Sunit Das, a PhD scholar at Department of Physics, IIT Kanpur, and I am one of the TAs. I mean, I think the two TA have been assigned for this short course. Okay, so before doing the actual TA session or question answer and so on, so I just want to have an estimate of uh, students from which departments or which fields they are joining, so that I can move or I can conduct the TA sessions accordingly. So can anyone, so everyone basically, so please, can you please tell which fields you are working on or which courses basically? So that will just help me to conduct the TA sessions. I mean, uh, that will give me an estimate ki how far I can go or how deeper I can go on that topics. So everybody, can you please tell your respective stream? So nobody interested to tell? Okay, so let me ask another question then. So, what are the expectations from these TA sessions? I mean, apart from that, NPTEL have some instruction to us definitely, but it is important to know from the actual audience as well. So anyone can just feel free to ask. Otherwise, there is no point of having these interactive sessions, right? These are for yours actually.
Good afternoon, sir.
Yeah, yeah. Good afternoon.
My name is Karan Thapa.
Yeah,
Sir, I have a question. One question.
yeah, yeah. Sure. Go ahead.
Can you explain वो जो फर्स्ट असाइनमेंट आया था ना
Mm-hmm.
तो उसमें तो क्या बोलते हैं कि 7 फैब को दिखा रहा था कि सबमिट करना है बट फिर उसमें ऑप्शन ही नहीं आया कि असाइनमेंट का फर्स्ट असाइनमेंट पे का हट गया ऑप्शन जिसमें कि हम अपलोड करते हैं ना अपनी फाइल
Mm-hmm.
या
Mm-hmm.
तो वो हट गया है वो
So you're
तो
talking
आप मुझे
about assignment one or zero.
Yeah, one वाला.
Okay, but okay. So I searched today, but I find no assignment actually in week one.
नहीं वीक वन के ना मुझे पूछना था कि असाइनमेंट क्या बोलते हैं वीक वन का जो है असाइनमेंट है वो 7 से पहले सबमिट करना है या उसी दिन जब भी आता है तब उसी दिन करना है
No, no. Anytime you can submit before the
बट
due date.
बट
Anytime you can.
ऑप्शंस तो नहीं आ रहा है असाइनमेंट वन का ना जो फाइल अपलोड करने का ना उसमें शो नहीं हो रहा है
So that might be a technical glitch. So better to contact actually NPTEL team. Okay. So these are not
ओके
handled by us. So all of
ओके
these things are handled by NPTEL team. So better to ask them actually.
ओके
Yeah.
Sir,
ओके थैंक
hello, sir.
Yeah. Yeah.
I am I Susma Kumari, Nalanda College of Engineering in Chandi.
Okay.
I, sir, one dot, please clear in assignment second. Question number two B. Compute the expectation value of the kinetic and potential energy for problem second in terms of the coherence factor UK and VK. Means assignment first is related to the.
Okay. So the point is, so as up to assignment two, it has been uploaded, but the due date is far away, right? So I think it is better to go ahead accordingly. So we'll first have a look at the assignment 0, probably homework 0, and then 1, and then 2. Okay. Otherwise, things is going to be messy. So,
Sir,
so
actually,
mhm.
that is the question number second. और ये मेंशन भी सेकंड में ही हो रहा है ना कि क्वेश्चन नंबर सेकंड में आप पोटेंशियल एनर्जी और काइनेटिक एनर्जी है जो आप कोहेरेंस यूके एंड वी के तो मींस आई डू नॉट फॉलो.
So okay. So you're talking about assignment 2, right?
यस सर.
Okay, so my point is ki let's have discussion and TA sessions up to assignment 1 first, right?
जी जी.
And then we can talk about assignment 2, right? So that is the point.
ओके
So
सर.
there should be a
ओके.
general progression of things. Okay, so any other questions or doubts? Okay, so let me share my screen. Okay, so let's just have a general introduction to that course, or some general features of those superconducting materials and all these basic things, and then accordingly we'll move forward, basically BCS theory and more evolving things basically. Okay. And I think homework 0 is also based on just general idea of what superconductivity is, how they behave in magnetic field, increasing temperature, etc.
Excuse me, sir.
Yeah, yeah,
Sir, I have a question.
go ahead.
So basically, yes, sir. So basically, the NPTEL is just posting the assignments and giving the due dates respectively. That on this particular day you have to submit these assignments. Like if a person has taken 3 courses, I have taken personally 3 courses. Then on 7 Feb only, I have to mean submit 3 into 2, 6 courses. Indeed, because of every assignment, the due is of 7 Feb only. So like I want to know that in on one day, like if we take off 7 Feb consideration, how many assignments have to be submitted? Like week 1 also due date is 7 Feb, week 2 is also due date 7 Feb. So means like how many weeks assignments dues are on a very particular day, like 3 4 weeks, like how?
Okay, so I do not have any clear idea how they fix the due dates, but I can tell you from my own experience. Last semester I also had a NPTEL course. So they used to set the due date accordingly. I mean, let's say this is week 1 going, so they will set the due date after week 1, or the at the very beginning of the week 2, right? So they never did the week 1 and week 2 due date same. So that just doesn't serve the purpose.
So
So
basically, like if I take an example, like this course I have also enrolled for the physical cyber computations also, and for bioinformatics also. So like the week 1 is still going, and because since the courses have started from the 22 Jan only, so but they have uploaded for the week 2 means content also, and also they have given their assignments also, and I have seen the due dates, it is like of 7 Feb only. So if I have 3 courses, so it means that I have to do 6 assignments on that particular day, like till that particular day, 7 Feb. So
mhm.
this was the reason.
Okay, so we cannot do anything about these things actually. These are all set by NPTEL. Okay, so we are just independent people who are conducting TA sessions. Our role is up to that, honestly. After that, nothing is taken care of by us. So that is point one. And point two is that one reason might be ki the courses are starting or have started on 22nd January. Now, if you count 7th February, is almost week two, right? So that's why they probably did that. 2 weeks time, and you have to submit both the assignments. So basically, you get time for week one assignments as well, right? You are getting extra time, almost 7 days extra time for week one assignment. So that's their point might be. Okay.
Okay, sir. And one more last question.
Mhm.
Sir, actually, since we are like not taking the classes at a physical mode, we are taking the NPTEL at online mode. So, though we would submit the answers for the assignments, but during the exam days, we want a means shorty for the answers that whether we have submitted it right or not. So, how we will get the answers, perfect answers of those assignments, like how the teacher would communicate with us, like we have a pre-recorded lectures only, we have not the teacher in our physical essence, so how the answers will be conveyed to us in a very detailed format also, that this answer will be solved in this way, because in the examination it is not that we memorize the question and particular that question only comes.
Okay, so that's an excellent point actually. So there are two, three things you have raised. So one point is key what may come or what may not come in the exam. That is not in our hand, not in your hand as well, right? That is completely will be done by instructor. Now coming to the second part, the detailed solution. Most of the cases, the detailed solution is will be provided to you. Okay, so there will be email from NPTEL with the link of that solution for assignment one, two, and so on and so forth. And third point, and most important probably of all this, is that uh, that is one of the reason we are conducting TA sessions. Okay, so TA sessions are meant to clear your issues regarding the courses or fundamentals of the courses. Some problems which are you are not able to do, or we may do it in a slightly different manner or some different aspects of it. So that is the point. And you can always ask us what is the regarding your problems. Basically, it doesn't really matter ki we are in week 2 and you have some confusion in week 1 questions, right? So you can always ask, but it has to be a linear progression. I mean, if you start asking week 4 questions, then we'll be in trouble. You guys will also will be in trouble, right? That's the point. I hope I answered your question, some of it at least, right?
So, sir, it means that after every due date, means the teacher, that particular respected teacher, will means uploaded the detailed solution of that assignment. That it's a mandatory for every individual teacher. It will
So
surely do it.
how they will do things, it is only their responsibility. Okay, but I'm telling from my experience. Okay, don't take my words as per rule book. Okay, so I did the NPTEL TSF last semester. So from my experience, I can tell you it really depends on the professor. Okay, how detailed that solution can be, or how detailed that solution they are trying to convey. But generally, professors are very conscious about these things, that we are having fully online mode of things. So they try to convey in more simpler manner and as detailed as they can. Sometimes they just also refer the books names and so on and so forth. Some links, maybe online PDF. So they are very conscious as per my experience. Now the point is key, even after that there might be some questions, might be some confusion. That's very normal, right? And for that, these TA sessions are the savior, or might play as a savior. At least we will try to uh, do that, or clear the confusions and so on. Right? That's the sole purpose of these online interactive sessions. Apart from this, probably you are not going to have any interactive session with the professors. Okay, they are just behind the walls, conducts everything, but uh, the TAs are the actual drivers of this assignment and all these things. At least if you talk about online interactive sessions, that's it. Okay.
Ji, okay, sir. Thank you so much, sir.
Yeah, yeah, welcome. Okay, so any other questions or confusions? I mean, these are really important because uh, these things should be clear from the day one. Day one means first day of TA session, let's say. Okay, so no questions? Okay, so let me start. So anyone have a question, or if you don't have any question, then please switch off your microphone so that becomes clear. Okay, so what is superconductivity? So superconductivity is, as the name suggests, it is superly conducting, right? You have some materials, let's say Hg. Hg, I am taking example because this was the first discovered superconductor. It was in 1911. So if you really cool the sample, you have some Hg sample, and you really going down to maybe Kelvin order temperature, right? So yeah, and you are observing the resistance versus temperature plot. So generally, as you decrease the temperature, the resistance or resistivity decreases. Now you will find some temperature where resistivity suddenly drops, and it's a very discontinuous behavior at some particular temperature dependent on that particular sample. You will find almost zero resistance. So this is zero, or it basically becomes non-detectable, right? So in your apparatus will have some limitation, least factor basically, and you are almost with zero temperatures. That is the superconducting phenomena basically. Now there are many general features or general properties of a superconductor. I'll touch briefly some of them basically. Okay, so again, so one point is superconductor. Sorry. And second point is you have suppose perfect conductor. So how do you distinguish between these two? So both of these carries current or have conductivity to a very high level. So basically resistance is almost zero for superconductor as well as the perfect conductor. So the distinction comes from the famous Meissner effect. So suppose you have some superconductor, and let me draw here. So you have some superconducting materials. So this is a down to Kelvin temperature, let's say around 10 Kelvin temperature. You have some sample, and it is superconducting. Now you apply magnetic field in the sample, right? So you are applying some magnetic field, B not equal to 0. Or okay, so there is another better way to do this. So you have some superconducting material, okay? So some superconducting material. Now you apply that magnetic field in that material, and then cool down to T less than Tc. Basically, in T less than Tc, that material becomes superconducting. So what will you observe is that, so the magnetic field will be deflected by that superconductor, okay, or that material. So when you cool down to T less than Tc, transition temperature of the superconductivity, then the magnetic field will be fully expelled by this superconducting material. So if you do this it another way, let's say you already have some superconductor. This was process 1, this was process 2, suppose. So again you are doing the similar thing but in a slightly different way. So you have some superconducting material and you already lowered it to T less than Tc. Okay, so that means it is already superconductor. So it becomes superconductor T less than Tc. Now you are applying magnetic field B not equal to 0. Even then you will find that magnetic field is being expelled by this material. So basically magnetic field is there, but it is not going, or it is magnetic field is not getting penetrated in the sample, right? So, and if you turn off this magnetic field in both of these, suppose B equal to 0 now, in both of the process you will find that it is again just a superconductor, right? It goes to the normal state, superconducting state. So this was the story of superconductor in a magnetic field. Now let's look at what happens with a perfect conductor. Okay, so in perfect conductor, so let's run the process 1. So suppose you have some perfect conducting material and then you apply magnetic field B not equal to 0. So in perfect conductor you will see that magnetic field is still penetrating in the system. Okay, now you cool down to T less than Tc in a perfect conductor. So now here just slightly technically wrong thing to when we say that T less than Tc, because perfect conductor doesn't have any superconducting transition temperature. So that's the distinction in fact we want to make between a perfect conductor and superconductor. So if you cool down enough, let's say we are not talking about Tc, but you are going to very low temperature, T nearly equal to 0 Kelvin. Okay, so then even then you will see that magnetic flux is penetrating, but there will be shielding current in the system. Shielding current means there will be circulating current in the system that will develop, that will basically try to resist the magnetic field or change in magnetic field basically. Okay, now if you run the process 2, this process 2, basically you have a sample and then you first go to T less than Tc or very low temperature T0 Kelvin almost, and then you apply magnetic field B not equal to 0. Then you will find that magnetic field is being expelled by this perfect conductor. Okay, and then if you turn off the magnetic field, that is B equal to 0, then you will find that sample is normal to this previous position. So what really happens is that so in the superconducting material, when you run this process 1 and process 2 and go back to that B equal to 0 limit, it just come back to its own previous position. Basically it remains superconductivity as long as you are in T less than Tc. Now in case of a perfect conductor, this state and this state are not same. So in this state you have a circulating current in the system, but in the process 2 you do not have any circulating current. As you switch off the magnetic field, it just becomes a perfect conductor as long as you are very low temperature, T around 0 Kelvin. So that is one of the distinction you can make between superconductor and a perfect conductor. So why do we need that distinction? Because if you run just a simple electrical resistance measurement, both superconductivity and perfect conductor both have resistance almost zero. So that this process cannot make a distinction between the superconductor and perfect conductor. That's why you need the process of inducing magnetic field and then switching off that magnetic field and see how they behave. Okay. So someone has raised the question. So can you please tell me what is your question or confusion? So no confusion? Okay. Okay, so this was the in superconducting system. This is called Meissner effect. Sorry for my very bad handwriting. So these Meissner effect essentially tells that whenever you are T less than Tc and you are applying a magnetic field B not equal to 0, so a superconductor will fully expel that magnetic field. Okay, so that means the magnetic susceptibility. Magnetic susceptibility chi is defined as the magnetization, the amount of magnetization, and divided by the applied field, right? So or more generally we define chi as del m del h, right? Now given the fact that magnetic field in the within the sample, so within sample B equal to 0, right? And we know B is applied field plus m, right? So up to some factor. In CGS unit it will be 4 pi. Now given that B equal to 0, that means H equal to minus 4 pi m, right? So from this we can say that the susceptibility or the magnetic susceptibility will be minus 1 by 4 pi, right? So it works as a perfect diamagnetic material. So whenever you have this magnetic susceptibility equal to minus 1 by 4 pi, it is perfect diamagnetic, or it shows perfect diamagnetism, right? So if you plot the magnetic field versus the magnetism in the system or magnetization, both are same things basically, I mean at least physically, you'll see that you have some straight line like this, and the slope is basically chi, right? Chi is del m del h. So that slope is determined by this minus 4 pi, or if you are in SI unit, then it will be perfectly minus 1, that slope. So that means it is a perfect diamagnetism. And this is the story of type 1. Okay, so there are mainly two types of superconductor. So one is type 1 and second is type 2. So this was for type 1. Now if you have some type 2 material, then you'll see that M versus H plot will somewhat look like so up to some critical field HC, you will have perfect diamagnetism. So this slope is -1 in SI unit. Okay, and after that, as you increase that magnetic field, the magnetization or the magnetization versus magnetic field curves have some this kind of slope. So that means it starts penetrating the uh, fields basically, and it starts deviating from the perfect diamagnetism in the system. So that is type 2. Okay, sorry, someone's question. No, but sorry, I don't understand your question. Hema Shankar study. This is not a course on data structure and algorithm. I mean, can you please clarify what do you mean? Can you please clarify, Hema? What do you mean? You can just unmute yourself and speak. Don't need to be on the chat box. Okay, sorry, I am not able to guess your problem. But anyway, okay. No, no, no. This is not a class about data structure and algorithm. No, no. This is a class on brief course on superconductivity. Okay, so we have just told the fact that uh, the Meissner effect, right? So just diamagnetism or the expelling of magnetic flux when the material is in superconducting situation. Now let's look at some electromagnetism of superconductor. So it's very basic because superconducting or superconductivity is basically a quantum mechanical phenomena. So whatever we do classically is just to have an estimate or just have an easy understanding of the phenomena or of that uh, observed phenomena basically. Otherwise, the phenomena of superconductivity is fully a cooperative phenomena and it has to be dealt with quantum uh, mechanics and as well as statistical mechanics. Okay, so let's start with one of the Maxwell's equation, rather fourth Maxwell's equation in electromagnetism. In fourth Maxwell's equation, we had curl of H equal to J current density plus epsilon del E del T, right? So what we are trying to do, we are trying to basically understand the fact that whenever you are, suppose this is a superconducting material and you are applying magnetic field, right? Now as it is a superconductor, it is going to expel that magnetic field. So that's what we are trying to understand. So if you take another curl of it, so this will be curl of J plus epsilon del T curl of electric field, right? Then you'll have Laplacian of H minus, sorry, plus gradient of divergence of H equal to curl of J plus epsilon del T curl of electric field. Now this term vanishes, right? That's another Maxwell's equation which says that divergence of magnetic field always vanish. This is basically, in physical, it means that no uh, magnetic monopole. No magnetic monopole exists basically. So then we get Laplacian of H minus curl of J minus epsilon del T curl of electric field. So if you just do a little bit of algebra, then again, so all algebra are basically just manipulating those Maxwell's equation, 4 Maxwell's equation basically. Then you will find finally that Laplacian of H will be J mu del H del T and plus epsilon mu del 2H del T2. So what is sigma here? Sigma is the conductivity. And mu is just usual permeability. So that's your equation of magnetic field, right? Now you can take an ansatz or guess solution basically, that you have magnetic field of the form. Let's assume that our magnetic field is directed along the z direction only, okay, just to make our life easier. And then exponential of so this is the ansatz solution, okay, where kappa will be k1 plus I k2. So I'm just stating the steps or writing down just the steps, like here to here there is some step jump or taking this ansatz solution, but you can actually do the full calculation and just arrive at the same conclusion. So I'm just trying to have a brief overview of all this, otherwise it will take much time. So k is basically a complex number, this k, and j is basically root over minus 1, right? So and then k square will be k1 square minus k2 square plus 2i k1 k2. It's just the complex operation, and you'll find that k2 is root over sigma mu omega by 2. Okay. So then, so from this thing, you will have that h equal to h0 z cap e to the power minus k2y. Why minus k2? Because here in k there is jk2, right? Jk2 and this j. So this makes minus k2y, and that sinusoidal form e to the power j q1y minus omega t. So, so from this part, you can see that the magnetic field or the amplitude of that magnetic field is getting reduced exponentially, right? As you increase the y, and k2 is definitely positive. It's a root thing. So, so it is somewhat like Meissner effect, that if you have magnetic field which is time dependent, right? Because otherwise we cannot make this answers. H is time dependent. So if you assume that H is time dependent and then start from fourth Maxwell equation and manipulate all those things, then you will get this somewhat like Meissner effect, which decreases as you go inside the sample. If you assume that in y direction the sample is there, let's say this is y direction and this is z direction where B is applied, right? So as you increase or as you go more and more inside the sample, the magnitude of the magnetic field decreases. So this is little like Meissner effect, but then here is a catch. In superconductors, Meissner effect tells that it doesn't really matter if you are applying AC magnetic field or DC magnetic field. It is going to expel both. But our theory on this part based on the only AC magnetic field, right? Only time dependent magnetic field you can deal with. Otherwise, you cannot write this thing. This will be zero already. This will also be zero. So then there comes another way to look at things for the superconductors. Okay, someone has a question. No. Okay. So let's look at the simple Drude model to explain the Meissner effect. So in Drude model says what? So if I have electron, let's say, and the force on electron is dp dt, right? Or the motion equation of motion, we can write it as dp dt. P is the momentum, and then let's say we have applied electric field. So this is force on the electron, and it also has some other part which is like this: p by tau. Tau is the scattering time. So whenever you have some conductor, let's say, and you are applying some electric field, then the equation of motion that governs the electron according to Drude model is the force part which is driving the electron, and another is the scattering part. So electrons are there and then they are basically coming from the ions, right? Ions of that material or the atoms. So electrons are going to collide with each other or the atoms as well, and that picture is captured by this term p by tau. So scattering time is basically the time. Suppose one electron starts here, and then it it is there, and it collides with some atom. Okay, So this minimal path is the distance between these two points before another collision. In time frame, it is tau. So basically, tau is the minimum time between two consecutive collisions, basically. Now, since it is a superconductor, we assume that there is no resistance, or we in fact get that from experience that there is no resistance. That means as if electrons are moving freely under the electric field. So then we can ignore the p by tau term. So then we will have dp dt equal to minus e electric field. So that's the for superconductor or perfect conductor, let's say. And we have current density J equal to n e velocity, right? N is the electron density, rather minus electronic charge, and v is the velocity. Okay, so we can write v p equal to mv, right? So then it will be minus ne p by m. Now if you, let's say, okay, fine, and from this equation we will use this equation. So let's take a derivative of j with respect to time. That means j dot will be minus ne by m p dot, right? So we'll use this equation. So that means it will be n e square by m e. J dot means this equation. And another, from Maxwell's equations, we know that curl of B equal to mu naught J, right? When we have when basically del E del T equal to 0, that means we have some static electric field rather than time dependent. So we'll use this equation. We can take a derivative of this with respect to time. Curl of B dot equal to mu naught J dot. So here in case of J dot, we will write curl of B dot by mu equal to n e square m sorry, slightly I need to make another step. So we'll take curl of this equations as well. J dot equal to n e square by m e. So curl of J dot equal to n e square by m curl of e. So then we can write curl of this equation. Curl of J dot means curl of B dot by mu 0 equal to n e square by m curl of E, right? So again, we can make just apply the vector equation, and curl of B dot by mu 0 equal to n e square by m, and curl of E is minus del B del T. This is another Maxwell's equation, minus del B del T. So you get Laplacian of B dot equal to 1 by alpha square B dot, where alpha square equal to m by n e square mu 0, this mu 0 basically. So that is according to Maxwell equation, we can arrive at this equation. So Laplacian of b dot equal to 1 by alpha square b dot. And this again have a solution. Let's say b is along the x direction. We'll take only one dimension in consider. Then we have a solution. You can check it, that b of x will be b naught e to the power minus x by alpha. Okay, so from this equation also we can see that magnetic field gets reduced as we penetrate the sample. As x increases, then magnetic field value gets decreased. Now from this also we can arrive at a very famous equation called London equation. So we had curl of okay, so we'll use these equations basically. So J equal to minus NEV equal to minus NEP by M, and we had minus P by V, sorry, M. Just give me a minute. Okay, we can actually directly use this equation. We don't need to do it over again. This equation. So curl of J dot, let's take curl of J dot equal to n square by m curl E. N square by m curl of E, right? So again apply that curl of E is given by minus del B del T. So n square by m del B del T. That means n square by m B dot. So after integrating both sides, this side and this side, with respect to T, we'll have curl of J equal to n square by m B. Okay, and then again we will apply Maxwell's equations basically. Curl of B equal to mu naught J, again assuming there is no electric field in around the system which depends on time, del E del T 0. Then we will get curl of, okay, so take another curl of this equation, curl of curl B mu naught curl J, right? And we are using this curl J, which will be curl of curl B by mu naught equal to n square by m B, right? So again we can find that this will be, so here we will have a extra minus sign, then minus Laplacian of b equal to minus n e square by m b. This will give me Laplacian of b equal to this is London's equation, and we usually express this by b by lambda square, where lambda square equal to n e square mu naught by m to the power half, minus half rather. So this equation gives you an estimate, or tells that again the same thing it tells. If you have a superconductor and you are applying magnetic field, as you go inside the sample, the magnetic field strength decreases, because this equation and then this equation also have the similar, this equation have the very similar form, right? Here we had b dot in terms equation in terms of b dot, which is time dependent, and here you have time independent. So this equation is valid for perfect conductor, because perfect conductor screens magnetic field which is only time dependent. Okay, that's a very subtle thing between perfect conductor and superconductor. Perfect conductor cannot screen the magnetic field which are time independent, but superconductor actually expels both time dependent and time independent magnetic field, basically AC and DC both. So that's why this equation governs the uh, Meissner effect for superconductor. Okay, so this doesn't tell about time dependence or time independence. They just tell that you have a magnetic field and that is going to decrease as b0 to the power minus x by lambda, and lambda is the characteristics length up to which you have some significant amount of magnetic field. So whenever you have suppose superconductor like this, right, so it is not going to be okay. So better to make one dimensional thing. So so let's say you have a superconductor of cylindrical shape and you are applying magnetic field, right? It will not be the case ki from this point onward there will be absolutely zero magnetic field. In reality it doesn't really happen. In reality what happens is that you have some characteristic length scale. Suppose you have this cylindrical superconductor, then up to maybe this scale there is some bit of magnetic field not equal to zero. Here as well, up to this scale not equal to zero, and as you keep in go inside the sample, the magnetic field value start decreasing. That's what this equation governs or tells us. Okay, so that was mainly the story of Meissner effect and the London equation governing that. Okay, so then there is another important observation in superconductivity phenomena, that we have a discontinuous jump in the specific heat of the sample. So if you, let's say, in normal sample, So specific, it means Cv. Cv is basically del E. E means internal energy, or at constant volume. So this is the temperature axis. So for a normal sample, if you start decreasing the temperature, you will and measure the Cv, then you will see somewhat like this, just a continuous decrease in the heat capacity. But for superconductor, you will see that Cv decreases as the temperature decreases, but then there is a sudden jump, and after this jump again start decreasing, and this jump actually exactly occurs at the uh, transition temperature of the sample. So this is the Cv behavior, and it tells us that there is some phenomena happening in the system around Tc, which makes that the specific heat, there is a jump in the system. Okay. And there is a detailed theory based on, again, some sorts of naive ideas of, or naive calculation of free energy and all this. uh, I'm telling this because, again, the end of the day, superconductivity is basically a purely quantum phenomenon. So, and now we are just trying to understand it on its simplest settings basically, and it is purely explained by a BCS theory. Okay, so next, okay, so have you guys solved the homework 0? If not, maybe I can go over a bit of that actually. So I'll not solve those exact problems because this is supposed to be an assignment, but so basically the overall ideas of those questions. So anyone can tell me that homework 0's due date have been passed, or it is still there? Anyone, please? Okay, so let me see once. Just a second, I need to log in. Okay, so there are some more just preliminary things such as isotope effect and then flux quantization phenomena, etc. So I'll just briefly go over that basically. Okay, so isotope effect, let's say. So isotope effect is basically as you vary the isotope of the sample. Let's say you have some sample, superconducting sample, and you are taking different isotope of that sample, right? Keeping that proton number same, right? You know the isotope thing. So and you are measuring basically TC of those different isotope. So what we usually observe is that TC varies as 1 by root over of m. So m is the mass of ion. Okay, so this is called isotope effect, where the transition temperature inversely varies as root over of mass of that particular isotope. And in BCS theory, we can understand this inverse behavior. Basically, what it really tells is that as you increase the mass, suppose the mass is getting increased, then TC will be lower. That means you need to go to more lower temperature to have the superconductivity phenomena, right? And in BCS theory, we understand that as follows. So phenomenologically, I am telling. So in sample there, let's say we have some electron and it is in some ionic environment, right? And there is some other electrons. It's just so many electrons they are there. Now, whenever a electron moves, suppose here to here, then a positive electron cloud gets created, right? Because ion, whenever an electron moves here, and in this place there is effectively a positive charge, or effectively a positive environment is there. Now there may be another electron coming from other side to fill this space, but before that, if another electron comes, meaning here you have electron which went there and it has some positive environment, positive ion environment rather created, and whenever another electrons comes in between, then there is effectively an attractive interaction, right? Because of this positive environment, and which is mainly created by the ionic ions of those materials. So isotope effect roughly tells you that if the ions are lighter, then they can easily move, right? Easily move. So if the ions are lighter, they can easily move, and then this positive environment gets created easily, so that there is a pairing mechanism. So in BCS theory, basically it says that two electrons gets paired and move as a single entity. Okay, and this single entity happens because of this creation of positive environment due to ions uh, created by this distortion of electrons. So if the ions or the mass of ions becomes lighter, then they can easily move, and this makes creation of Cooper pair. This electron pair we call Cooper pair. Creation of Cooper pair is easier. Now, as this creation of Cooper pair is easier, that means you need you need, or you may have superconductivity at relatively high temperature. Okay, so that is the rationale. So you have low mass, that dictates that ion are lighter, they can easily move, that will help in the creation of Cooper pair. And as the creation of Cooper pair is being favored, so superconductivity may show up in relatively higher temperature. That means M is inversely proportional to Tc. That much we can tell from this phenomenological explanation. But why it exactly goes as root over M, that comes from the detailed calculation of BCS theory. Okay, but roughly and phenomenologically, this is the isotope effect. So as you take more heavier atoms or heavier ions of the same material, you have to go to really low temperature to have that superconductivity one. And there is another concept called flux quantization. So we'll again go back to the M versus H curve of type 1 and type 2. So for M versus H, for type 1, it was perfectly diamagnetic, and chi was -1 in SI unit. And for type 2, it was somewhat like this, and then it was increasing, right? So type 2, and this was the magnetic field, some critical magnetic field. After that, it starts, the magnetic flux starts penetrating the sample. So simply we can understand this as follows. So if this is type 1, then at all magnetic field, as long as it is a superconductor, it will expel that magnetic field. Okay, but if it is type 2, then if magnetic field is below some critical magnetic field, that means you are essentially in this zone. Okay, then it will definitely expel that magnetic field as type 1. But as you increase that magnetic field, so let's say H greater than Hc, that means this particular zone, right? In this particular zone, uh, the magnetic field starts penetrating slowly. And in sufficiently high magnetic field, definitely it will, superconductivity will get lost. So basically, even in superconducting case, for type 2 superconductor, there is some amount of magnetic flux. Magnetic flux is not equal to 0, right? So it is above Hc, critical temperature, for type 2. And it turns out that this magnetic flux through the through this sample, that it gets penetrated above the critical temperature, it is quantized in terms of fundamental flux unit, and the unit for fundamental flux is probably H by E, H by E, okay, that will be 2E basically. So this is the and this n is the 1 2 3 integer number. So the flux through each of these circles, or we in type 2 superconducting case we call it vortex. Each vortex contains magnetic flux which is quantized in units of fundamental flux, H by 2E. Okay, 2 is the electronic charge of Cooper pair, because as we discussed above, that in superconductivity there is 2 electron gets clubbed and then behaves as if a single entity. So that is the basic units of flux, phi 0. So there will be n. So this phenomena that the flux inside the sample is quantized in units of fundamental flux quantity, phi 0, which is h by 2e. This phenomena is known as flux quantization. Okay, and it has a detailed analysis based on quantum mechanics. We can show that indeed flux through the sample is quantized. Okay, so that's what roughly the content was for at least week 0 and week 1 maybe. Yeah, till week 1. I will go to week 2 in the next session. So I'll maybe I'll attend some of your questions that you may have and then come back to this actually. So basically I'm not trying to go to week 2 because before doing things of week 1 and 0, it will not be okay, right? So any of you have any questions? Any questions? Okay. Okay, so just an aside, yeah, tell me. Hello.
Hello, sir.
Yeah, yeah.
ये please draw a graph between density of states and energy.
For a superconductor or for
Yes,
normal
sir.
state?
For a superconductor.
Okay. Okay, I'll draw. Any more questions? Anyone? So okay, so I just want to tell one thing is that so first session always becomes a bit messier because just getting things in process and then how do I progress like like I came to know that 7th February is the last date for both of these things, right? So I hope that from next PA session things will be much smoother and prepared things. Okay, so yeah, it might look a bit messier and then unorganized in the first lecture at least. Okay, so for density of states, so usually normally if you take an 3D sample, if it is DOS, let's say, and then it is a function of energy epsilon, then you will have this kind of normal free electron, let's say, then it behaves as root epsilon. Okay, so this is for normal free electron, let's say. Or normal metal, because metal in metals the electrons are effectively free to conduct. But if we have some superconducting phenomena, then So for a superconductor, the dose versus epsilon or energy looks like this, and here this is the epsilon F. This is Fermi energy. Okay, so what this necessarily tells is that around the Fermi energy there is no density of states. Okay, so that's what it physically means. Now it has a nice explanation in the BCS theory that electrons are basically absorb some amount of energy, which is actually h bar omega, and omega is the related to phonon frequency, and it absorbs h bar omega amount of energy so that it excites and then overcome this gap to form a Cooper pair basically. And this phonon frequency again states the fact that in superconductivity phenomena there is an effect of ions as well, right? As we seen in the isotope effect here. Isotope effect is nothing but the effect of ion or ionic mass on the superconducting transition temperature. So this naturally comes in the construction of BCS theory. So any question from any other person?
Excuse me, sir.
Yeah, yeah.
Sir, when means like after the 7th of Feb, when the due dates of this assignment will be gone, will you upload all the answers of these assignments on the portal so
No,
that we can check?
that will be shared by NPTEL team. Okay, so usually professors write down the answers of that solution, and either you will anyway have the link on the portal, and they also I think email you. Okay, all the registered students. Okay, so after due date they automatically email a solution of those particular assignments.
Means like sir, like if the option is like of MCQs in a theoretical part, then the direct option we could understand that this is the answer. But if it is like in a mathematical aspect, so did the do the team explain further that answer also, that how it come like in detail explanation also it gives the means answer key.
Okay, so you are talking about the
Uh,
so basically calculation behind that MCQ answer, right?
like sir, in this assignments also some are theoretical based, so this would be very easy for us to analyze through the answer keys when the NPTEL team will submit. But some are like of the numerical basis that we have to answer. So the team will also send that particular detailed format answers also of that numerical one.
No, so NPTEL team doesn't do anything, okay? So it all depends on the professor that who is preparing that answer sheets. So if he prepares a detailed answer sheet, then that's fine. They will prepare, but it really depends what professor wants to do. But again, so from my experience, I can tell you is that professors are very concerned about all these things. Okay, they have the experience as well as they are informed of all these difficulties. So whenever they prepare any solution, they took care of everything almost. At least they try to, that I have seen. But even after that, if anything is there, any confusion, then these TA sessions are the things which you can use. Okay. So is you so is that answered? Okay. Okay, since I have lots of time, so let's derive this flux quantization concept actually. Okay, how it comes. So basically, in flux quantization, what happens? Let's say I have some cylindrical uh, form of superconductor, and then there is magnetic field, right? Then after certain magnetic field strength, which is Hc, there is a formation of vortex. Formation of vortex where the flux gets inside the sample. Okay, and just to derive that vortex formation or the flux quantization, we'll assume that the whole state of superconductivity is determined or represented by some macro wave function e to the power I phi. So this is the phase factor, and this is simply the wave function part. And this psi 0 square is proportional to ns. Ns means the density of yeah, Cooper pairs. So again, so we are basically entering a quantum mechanical formulation, right? We are representing the whole state of superconductivity by a single wave function. But again, so the point is that this is not the state for the electrons. Okay, so the superconductivity is a cooperative phenomena. So the electrons or any other particles which are there in the system, not in case of superconductivity, let's say, but so in general, cooperative phenomena is that which systems works in a cooperation. So in case of superconductivity, electrons forms Cooper pair and then they conduct like there is no resistance, right? Other example of cooperative phenomena might be the phenomena of ferromagnetism, let's say. In ferromagnetism, most of the spins or at least magnetization is non-zero, right? So then spins are up. At least effectively in the system, there is up spin or down spin. So again, the spins, electronic spins works in cooperation and gives a macro phenomena. Macro phenomena means microscopically there are so many things happening, but macroscopically we can see this ferromagnetism or paramagnetism or even diamagnetism. All these are cooperative phenomena. So this is a very important point, that this psi doesn't represent the electronic wave function, rather the state of superconductivity. So we'll calculate probability density Js. S means superconducting system. So so this will be 2m. This is just I am writing the formula for probability, quantum mechanical formula for probability density. Psi star grad psi minus, psi grad psi star minus mu naught e square by m a psi square. Okay, so this A is the vector potential. Vector potential representing B. Magnetic field means curls of A, right? So in presence of magnetic field, the probability density or the current density rather probability current density becomes like this. Okay. And another interesting thing to note is that here E doesn't really means electronic charge. Okay, E means 2 of electronic charge, because the formation of Cooper pair makes the 2 electrons as a single entity. Similarly, M is the 2 of Me. This is the mass of electron. 1 electron. Again, this is the 2E. So let's evaluate this equation first, Js. So grad psi will be grad of psi 0 e to the power I phi, and psi 0 is doesn't depend on the gradient or the spatial. So psi 0 doesn't have any spatial dependence. Spatial dependent is incorporated in the phi, okay, phase factor. So basically grad psi 0 will be 0. Sorry. So this will be basically I psi grad phi, right? Because grad psi 0 equal to 0. If we replace this, then we'll have Js equal to minus IH by 2m mod psi square gradient of phi, and then minus 2 electron okay, so there will be no 2. So here we have used that just a second. Just got freezed. Okay. So this ns is basically coming from the ns equal to mod psi 0 square. Okay. So then we can write this as h bar e by 2m, and there will be 2 here coming from there is psi star grad psi and then grad psi star psi, okay, from this one. So we'll have mod psi square gradient of phi minus p square mu naught ns by m. Okay, now we'll calculate a closed loop integral of this current density. So h bar E by me mod psi square grad phi dot dl minus 2e square mu naught ns me a dot dl. So let's say I had this superconducting cylindrical material, and I am choosing this a closed circle. Okay, this is dl, some elementary part of it. And note that here I have switched to mass of electrons and mass of electronic charge. Okay, so E goes to 2E actually, and M is 2me. I have used that. That's why two factors here, two factors are gone, and there is another two factors, etc. So we choose the current loop in such a way that there is no current on the loop, current density rather. So if you choose the loop outside the sample, basically covering the whole area of that sample, then here is no current, right? Because the current in the sample, if it is there, then it will be within the sample, not outside. So then J dot dl is definitely 0. And then we'll have EH bar by me mod psi square closed circle grad phi dot dl minus 2e square mu 0 ns by me a dot dl. Okay, so if we do a little bit of algebra, then we'll have closed loop integral of a dot dl equal to h bar by 2e closed loop integral of grad phi dot dl. Okay, and this a dot dl is basically v dot ds, right? If we apply that Stokes theorem, so basically a dot dl can be proved to be on the surface. This is on the closed integral v dot ds, right? And this is basically flux, magnetic flux. So phi equal to v dot ds equal to h bar by 2e and grad phi dot dl. Now the wave function that we took, psi 0 e to the power plus I phi, this wave function has to be single valued. So for a single valued wave function, this particular parameter becomes 2 pi n. So okay, so this particular thing, 2 pi in the multiple of 2 pi, where n is 1, 2, 3, etc. Right? So then we'll have h pi 2e into 2 pi n. Sorry, not close. So then magnetic flux equal to h by 2e into n equal to n phi 0, where phi 0 is h by 2e. So the magnetic flux that a vortex carries within itself, this vortex, is in the integer multiple of fundamental flux quantity phi 0. So that's what it tells basically. So that means magnetic flux inside the vortex is quantized in integer multiples of phi 0. Okay. So I have actually skipped a lot of steps in between, but the essential idea was to tell you is that whatever we are discussing phenomenologically, all these flux quantization, jump in the specific heat, or gap in the density of state at the Fermi level, all these things actually can be derived from the quantum mechanical framework. Okay, those things can be messy and lengthy, but in principle everything is derived. Okay, so will I get any session before 7th February? Just to, yeah, I'll get another session on 4th February. So on that day, I will discuss the uh, assignment 2, mainly focus on the assignment 2. Okay. So any questions so far? No questions? Okay. So by the way, I just have a question. Ki you guys went through the up to at least week 1 lectures, right? All of you?
Yes.
Okay, that's fine. Mhm. Okay, so what else can I tell phenomenologically? Because I'm not going to do any mathematics today, much of mathematics basically. Just give me a second. Let's me have a look at the homework 0. So you guys have assignment 1. I mean, today I searched, I went to that course portal, but I didn't see any assignment 1. The link is there, but then the link shows something else. Any of you have assignment 1?
Date of submission of assignment 1 is 7th February, but it is unable to see in website.
Okay. Okay, so that's a problem actually. So you guys should actually mail NPTEL, otherwise they will miss it. I mean, I think they do not know that assignment 1 is not there, or it is there, but the PDF is something else, not assignment 1.
Okay, sir.
Yeah, you guys mail and NPTEL will definitely respond. Okay, so any other questions or any confusions? Just please tell me. Otherwise, I think we can stop here for today at least, and then we'll continue on 4th February. And yeah, I mean, before that, so it is actually better to know what is your expectation from these TA sessions and what are the problems. Problems doesn't have to be really only associated with that the assignment questions that you need to solve or submit, but in general, in concept wise or anything else, right? So in this course or in any other NPTEL online course, the TA sessions are the only thing that you get to have an interaction with the TAs basically. We are not instructors, definitely. We're just students, but still we'll try to answer it. Probably we can answer, most likely at least. So no questions. Okay. So only one request is there. Please be interactive. Otherwise, these sessions, I mean, we'll just have some problems from next day. That this is the first day, so I don't want to have any all these mathematics problems. So I just went through the just phenomenology and as much little mathematics as I can. But otherwise, mostly, I mean, the questions will be either mathematics or some MCQ. Uh, I do not think they will give some descriptive questions in the exam at least. So yeah, I mean, being interactive and posting your doubts is really necessary. That way we will also feel good ki we are trying or we are at least helping you guys. Otherwise, I'll just come and solve few problems maybe, but I will not get to know ki how much of this is helping. It will help to solve the assignments. That I can definitely tell, because I'll see the assignments and then prepare accordingly. But the course is not necessarily only about solving some numerical problems. It's also about clearing the fundamentals, right? So yeah, okay. So let's end today's meeting here, and thank you for joining. I hope you will be interactive next time onwards. Okay, so I'm stopping